Are you okay?
Yes, I'm good.
All
Thank you.
right. And finally, our lecture today with the 18 electron rule and how to count them. Examples and ask the class about some questions which we have learned already last week. Suppose if I were to give a complex of can you all see that? It's tris oxalato vanadate. And what is the oxidation state of this vanadium? Oxalate is an anionic ligand. And when I put that one, what should be the oxidation state of vanadium? These are the kind of questions that we'll be expecting in the exam.
+3.
Absolutely correct. Okay. Tungsten. It's an octacyano-tungstate. What should be the oxidation state of tungsten in this case?
Is it +5?
You are correct. That is +5. Let me put another one. Fe2CO9. What should be the oxidation state of iron in this? What kind of a ligand is CO? Is it neutral or anionic ligand? Any answer for this? If it is a neutral ligand and if there is no charge, what should be the oxidation state of iron then? Shouldn't it be 0? Would you all agree? That is iron in 0 state. All carbonyl complexes, whether you have nickel carbonyl, iron carbonyl, and if you have no other ligand. If you have a different ligand, of course, the oxidation state may be different. But if you have purely neutral ligand, like aqua complexes, amine complexes, triphenyl phosphine complexes, these are all neutral ligands. And when you have a neutral ligand, oxidation state of the metal is 0. Okay. Let me do one more thing. Suppose I give you a complex like this. That's a neutral complex. You have carbonyls, you have an ethylene ligand, and you have 2 triphenyl phosphines or trialkyl phosphines. What should be the oxidation state of rhenium in this?
Sorry, which element did you say?
Rhenium,
Okay.
REA. We'll be walking all over the periodic table, folks. That's what inorganic chemistry is all about. Dealing with 3 or 4 elements, we have to deal with 100 more elements here. So what should be the oxidation state of rhenium in this? I can give you an answer, but that, you may not even try then. So to answer that question, this is a neutral complex. What is CO? Is it neutral or anionic ligand?
Would CO be neutral here?
That's correct. CO is always neutral, not here, anywhere. All right, how about trialkyl phosphine, PR3s? What did we say last week? Neutral too, right? We can be wrong, but at least we should try. How about alkene? Ethylene, for example. What is it? Is it neutral or anionic ligand? There's no charge on ethylene, right?
Is that also neutral?
That's also neutral. So the only thing that determines the fate of rhenium oxidation state is the methyl. Methyl is CH3 minus, right? That's an anionic ligand. So if CH3 minus is an anionic ligand, and if there is only one, what should be the charge on rhenium then for the complex to be neutral?
+1?
+1, that is correct. So in this complex, the rhenium is +1. So even if the complex looks really complex with so many ligands, we just have to be patient, go one by one, answer whether it's neutral or anionic. That is what determines the oxidation state. So that complex rhenium is +1. The oxidation state determination is very important, because if we don't get that right, then whatever we're going to teach you on the 18 electron rule might look like Greek and Latin for you. Okay, it's very important that we need to master finding the states of metals in various situations, which is what I tried to go over in the past 5 minutes or so. Any questions on this? Yes.
Is CH3 always a -1 charge?
That is correct.
Okay.
That's a methyl ligand. If you have a double bond or a triple bond, those are anionic complexes. I'll also give you some other list. If you have allyls, oxides, imides, alkaline dienes, alkoxides, thiolates, amides, and phosphides, these are all anionic ligands. We will go through that list in a minute, but is this clear to all of you so far? The next thing that I need to do is, in the lecture that we posted on the Canvas, we did talk about some isomerization, some isomers, but that was not an extended list. So I'd like to go over different types of isomerism that you can have in coordination complexes. But before I do that, are there any questions so far on these oxidation states? Are you all okay? Okay. Because some of you, I don't see your face, so I don't even know what you are doing, what you are thinking. At least if you nod your head, I can see it, but I can't see for majority of you because you prefer not to use the video. But that's why I keep asking that question. All right, so if that is the case, I would assume that you all are okay with this, and then move on with different types of isomerism, okay? This is very important to recognize. The first one is what I call ionization isomerism. Again, before we continue with this, we all agree on the definition of isomers, right? They have the same chemical formula, but different arrangement of ligands and the counter ions. All right. It could be geometric isomerism. It could be a structural isomerism, or it could be linkage isomerism. So there are different types of isomerism that you have in the complexes. And depending on what you have, the color and the properties of the complexes are going to be different. So let me write down two of those complexes. For example, if I have Cr NH3 5Cl SO4 and Cr NH3 5 SO4 Cl. If you look at these two complexes, they have the same formula, right? Except the placement of the ligands is different here. So we call these two ionization isomers because when you dissolve these complexes in water, the composition of the cation and anion is going to be different. For example, if you were to dissolve the top complex in water, the anionic ligand that gets dissociated here is a sulfate. So one way to test the sulfate is add some barium ion and you will see a precipitate of barium sulfate. That's how you know that sulfate is not in the coordination sphere, but it's outside the coordination sphere. On the other hand, if you look at the second complex, the CrNH3 5SO4 and Cl, in this case, Cl is not a part of the coordination sphere. It is outside the coordination sphere. It's a counter ion. So when you dissolve this, your solution will have predominantly chloride ions as opposed to having sulfate in the first case. That's the difference. So that's why whenever you see two isomers that will result in the formation of different types of anions and cations, you classify them as ionization isomers. Am I clear here? Yeah. Sometimes in the exam, we'll give you a pair of complexes and want you to identify what type of isomers these are. So these are the types we're going through. But so this one, second complex, for example, when you add silver nitrate, you will see a precipitate, which is silver chloride. On the other hand, the first one, when you add barium nitrate, you get a sulfate, barium sulfate precipitate. That's how people know where the counter ions are. Am I clear here, folks? The second type of isomerism is called hydrate isomerism. Give you some examples of the hydrate isomerism. And then I have one. You can also have look at those three complexes. What is common between them and what is different between them?
With the first one, how many chlorines is that?
3 chlorines.
3? Okay.
All of them have 3 chlorines.
Okay.
Chlorine to water, they're all same because they're isomers, right? They should have the same formula. The arrangement is different though. In the first one, I have all the waters inside the coordination sphere. In the second and third example, I have water coming as a water of crystallization or water of hydration, whatever your teachers were telling you. Okay. So the complex. So such complexes are designated as hydrate isomers because of the placement of the water. In fact, the first complex looks gray-blue, And the second complex looks light green in the color, and the third complex looks really dark green. Okay, so you can see the colors are very different, although the formula is still the same. One thing that you may be getting by now is most of these coordination complexes have a characteristic color. In other words, they have absorption range. Okay, so in the advanced inorganic chemistry, we will understand why these complexes are colored. But for now, in this course, it is enough to recognize that the coordination complexes are distinctly different. So that is what makes them very interesting. Am I clear here, folks? The third type of isomerism that we can get in the coordination complexes is what we call linkage isomerism. So this isomerism is seen whenever you have a ligand that is ambidentate. Ambidentate ligands are those that can use more than one atom in the ligand to bind with the transition metal. For example, if you have NO2 minus, the NO2 can bind using the nitrogen end of the molecule, in which case it is the metal versus NO, that type of. These are called nitro complexes. So whenever the nitrogen is used for binding with the metal, it's called a nitro complex. On the other hand, the metal can also bond with the oxygen end of the nitrate, in which case we call this nitrito complex. See the difference between them? So whenever you have a ligand that can use more than one atom in its formula to bind with a metal, you will have the possibility of recognizing the linkage isomers. So an example of this is, for example, CO NH3 5 ONO Cl2. This complex is a red one, so it's called a red nitrito complex. On the other hand, you can also have CO NH3 5 NO2 and Cl2 again, same formula. This one is an yellow complex, yellow nitro complex. Am I making sense here, folks? Especially if you have amino acids, right? You have nitrogen as well as oxygen. So you can have a bonding through nitrogen or oxygen. So those are all the cases where you can have more than one atom into the bond. Similarly, if you have CN minus, CN minus can use either carbon or nitrogen to bind with the metal. What is NC called, NC minus called? CN minus is called cyanide, and NC minus should be called? Any thoughts? NC minus called. Have you seen NC minus in your organic chemistry courses? No? Have you seen
Isocyanide?
CH3NC, methyl isocyanide? That's correct. NC minus is called isocyanide. So when you use that as a ligand, you say isocyano. If you use cyanide with C, so both are very different complexes. As you can see here, the colors are going to be different, the activity is going to be different, and a lot of physical and chemical properties of the complexes depend very sensitively on how the ligand is connected. Am I clear here, folks? So whenever a pair of complexes are given to you, you should be able to recognize the type of isomerism that they have. All right. Okay. You can also have stereoisomerism. We'll go over the examples of stereoisomerism very quickly. This stereoisomerism arises because of the spatial orientation of the ligands around the metal atom. Typically, stereoisomerism is two types. One is called geometric isomerism. The other one is called optical isomerism. So coordination complexes can have both geometric and optical isomers. So in the case of geometric, we have cis, trans, or FAC-MER isomerism. We'll go over each one of them. Okay. In the optical, we have R or L and R, left or right rotation of the polarized light, which you already know in organic chemistry. You must have heard a lot about this stereoisomerism, right? Okay, so we'll go through some examples here and then see how cis and trans are done and how the optical isomerism is recognized. Is this clear to all of you so far? Any questions? On the board. So these are all the variety of isomerism in the coordination complexes. So let's start with geometric isomerism. Geometric isomerism is most prevalent in square planar and octahedral complexes. Okay. Geometric isomerism does not show up in linear or tetrahedral complexes, because in tetrahedral, all positions are identical. So there will be no cis-trans isomerism in tetrahedral complexes. So let's take the examples of both square planar and octahedral complexes and show you how a cis-trans isomerism can occur. So let's talk about PtCl2 NH3 complex. Dichlorodimine platinum 2 complex. Okay, this is a square planar complex. If you followed my lecture previously, you must have noticed that if the electronic configuration of the metal is D8, and if it is a transition metal, more likely it will adopt a square planar configuration. So when you write the square planar geometry, this is, you start with platinum in the middle and you start filling the corners. Then, so put the 1 chlorine here, first one, and you have then two choices for the placement of the second chlorine atom. So you have Cl and Cl. The second chlorine atom would be on the same side or it could be in the diagonally opposite position. So if it is in the same side, we call this cis. And if it is on the opposite side, it's called trans. The remaining ligands occupy the leftover position. So the left one is called the cis complex. The right one is called the trans complex. Although the difference looks very trivial, you know, you might be thinking, what's the point here? You know, having the same side or maybe a different side, should that really matter? It does. In fact, the difference in the biological properties of these two complexes is like day and night. For example, cisplatin, or where the chlorines and the amines are arranged on the cis position, is an active cancer drug. Transplatin has absolutely no chemotherapeutic value for cancer. That's how different they are. So when you make the complex, you have to make a cis complex rather than trans. Unfortunately, when you make the complexes, you always end up having mixtures of both cis and trans. That's a big pain in the neck for pharmaceutical industries to separate them out. So there are two aspects here. One is you're using platinum. To begin with, platinum is an expensive drug. And the process to separate the cis and trans is again an additional problem. So that's the reason why some of these chemotherapeutic platinum-based drugs are so expensive. I myself had an opportunity to help Johnson & Matthey, a company that specializes in making these complexes. I have had a project with them for almost 3 years in coming up with efficient ways of preferably making the cisplatin, and we were successful. It was not easy, it was very challenging, but we were able to provide conditions that will predominantly, not completely, not exclusively, but predominantly cisplatin. So the further purification steps are minimized. Okay. So these are extremely important isomerisms. Not only the biological properties, but also the chemical properties, catalytic properties of the complexes depend quite sensitively on this stereoisomerism of these complexes. Is this clear to all of you folks? This is trans isomerism.
Yes, Professor, I have a question. How do you separate the cis from the trans?
It's not an easy process, but unfortunately, I can't discuss that because I have a confidentiality agreement with the Johnson & Matthey. Okay. I wish I could tell you, I know how to do this, but I'm not allowed to say that. If you can come back after 5 years when my confidentiality agreement expires with Johnson & Matthey, I can explain to you. It's not a straightforward method. It requires a little bit of chemical manipulations. In fact, starting precursors are entirely different. What Johnson & Matthey was doing, we changed the process very completely. We said, if you do the same thing what they have been doing for the last 30, 40 years, this is the mess that you end up with. And if you keep refining the same process, it's like the Einstein's definition of a stupid, right? You repeat the same experiment, and if you expect every time a different result, that is the definition of stupidity. So what we said was we don't want to fall in that, so we completely started out in a very different way. Sorry for disappointing you, Gurveer.
It's okay. I'll come back in 5 years.
I hope you understand. Okay, all right. Any other questions, folks? But the answer is yes, you can separate them. There are ways of separating them. All right. Okay. Now moving on. Can I have a similar isomerism in octahedral complexes? let's say I have an octahedral complex in the same way with 4 amines and 2 chlorines. So this is dichlorotetramine platinum 2 complex. Clearly we have 6 ligands here. So the most preferred geometry when you have 6 ligands is an octahedral geometry. So here again, you can have a situation where you will have 2 different arrangements. You have platinum, the platinum. So you can have the chlorines on the opposite ends, or you can have a chlorine on the same side of the octahedra. Do you see that difference there? In here, the chlorines are in the opposite apical centers of the octahedra, but in this, the chlorines are just next to each other. So this complex is called as a cis1, and this is the trans. Okay, this cis-trans isomerism in octahedral complexes happens when you have 4 ligands of one type and 2 ligands of other type. So whenever you have a metal and L1, 2, a ligand 1, 2, and a ligand 2, 4. So 2 of one type of ligand and 4 of other type of ligand. Am I clear here, folks? To summarize, cis-trans isomerism cannot exist in linear and tetrahedral complexes. The square planar and octahedral complexes can show cis-trans isomerism in some cases. Okay, that means you have to have 2 ligands of the same type, 4 of a different one, to see a cis-trans isomerism. Similarly, if you have only one type of a ligand, for example, if I have Cl and NH3,3. So you have 1 chloride and 3 amines. Well, this will not, mind you, this will not show cis-trans isomerism because you need to have 2 of the same kind in the square planar complexes. So by looking at the possibilities, there is only one way of writing this complex. There are no 2 ways of doing it. For that reason, this complex will not exhibit cis-trans isomerism. So whenever a complex is given to you in the formula, you should be able to recognize whether or not it is possible to achieve cis-trans isomerism. Any questions so far? Are you okay? The other type of isomerism that you may have in coordination complexes is what we call Fachner isomerism. So this is called facial and meridian isomerism. Okay, so when would you see this? This is generally possible when you have a metal and 3 of one type of a ligand and 3 of another type of ligand. So of the 6 ligands, if you have 3 of one kind and 3 of other kind, that is when you might get the Fachner isomerism. So let me show you how the Fach and the mer isomers are there by taking an example of CO NH3,3 Cl3. Trichloro, triamine, cobalt 3 complex. This is a neutral complex, the cobalt in the oxidation state of 3. All right, so what are the different ways of arranging these ligands around the metal? So if you look at the octahedra, two possibilities, right? So I can have cobalt in both cases in the middle. I can have the chlorines Cl, 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 and NH3, NH3, NH3. That's one possibility, right? Or I can have Cl, 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 and NH3, NH3, NH3. Now, if you look at this very carefully, what you find is, if you look at these three chlorines, they are in the face of a triangle on one face of the octahedra, right? So this is called a FAC isomer. That means it's on the face of the triangle of the octahedra. On the other hand, if you look at the Cl, Cl, and Cl, you can draw an arc like a meridian, and these are the Cls that stay on the meridian. So this is called a mer isomer. FAC-mer isomerism is not possible when you have ligands not in 3:3 ratio. If it is 2:4 or 5:1, you will not get FAC-mer isomerism. FAC-mer isomerism is possible only if you have 3 of one kind of a ligand and the remaining 3 of another kind of a ligand. I'll give you a minute to write down those notes. I'm giving you the definitions, examples, and the pictures of how these isomers can be recognized.
Sorry,
Yes,
I have a question.
sure.
So it be 3-3, right?
Yeah, 3:3.
So if you have 3 of one, but you have 2 of one and 1 of another, like a third one, does that still apply or no?
Yeah, you can still have, because even if you have different ligands here, right? Not NH3s, but you must have
Right.
3 of the same kind. Then you
Okay.
have one in face and one in the meridian. Yes.
Okay, understood. Thank you.
Thank you very much for asking that question. Yes. I'm glad that you're following. I'm sure all of you are following this too.
Professor,
Sure.
I have another question.
Yes, sir.
Could you have the NH3 at the top and bottom, like 2 NH3s instead of the chlorine?
Hmm? You mean NH3 here, NH3 there,
Yes,
and then another NH3 here, right?
yes.
Then automatically you have chlorines on that one, whether you have chlorines or ammonia, right? An
understand.
octahedra is a symmetric object, so they still be meridian.
Got it.
Good question, yes. Okay, so far. All right, so the one last type of isomerism is what we call the optical isomerism. From organic chemistry, when do we call two compounds optical isomers? Any recollection from your courses?
It when they're enantiomers.
Correct. Enantiomers is a different way of calling the optical isomers. But what is the property, or what makes those enantiomers optical isomers?
Chirality.
Chiral. What is chiral?
When there's different attachments to one main atom.
That's correct. But beyond that, there is one more critical thing.
To rotate light.
They rotate like that is a consequence of the optical isomers, not the definition, right? For two compounds to be called optical isomers, I'm sure you must have heard, but you refuse to connect the dots. Remember the word non-superimposable mirror images? If you take a compound and its mirror image, and if you find the mirror image and the original source are non-superimposable, then we say they are optical isomers. And we call them enantiomers, we call them chiral. These are all the different ways of describing, but the main important aspect of an optical isomer is the presence of non-superimposable mirror images. That means these two structures that you're dealing with must be the mirror images of each other, but you will not be able to superimpose them. Okay. All right. Now that we know a little bit of symmetry and point group classifications, we can perhaps use that knowledge to identify the presence or absence of optical isomerism. I would claim that if a structure is highly symmetric, there's no way you're going to have optical isomerism. Let's say a linear molecule. Can you ever have a linear molecule exhibiting optical isomerism? If there is a plane of symmetry, then it cannot have optical isomers. How about square planar complexes? Can you have optical isomerism in square planar complexes? Like, for example, if I were to write a nickel, chlorine, bromine, fluorine, and iodine, this complex, square planar, can it have optical isomerism? Does it have a plane of symmetry? What did we say about planar molecules when we were talking about point groups?
It's just a plane of the molecule itself.
Wonderful. Thank you very much, Michael. That's the reason why I keep using those words. All planar molecules at least have one plane of symmetry, that is the molecular plane itself. And then I claim that if a molecule has a plane of symmetry, it cannot have optical isomerism. So by definition, then you will never look for optical isomers either in linear complexes or in square planar complexes. Does that make sense to you? I would also claim that if you have a tetrahedral molecule, let's say can this have optical isomerism? It's a tetrahedral. Does it have a plane of symmetry? It has, right? It has at least one plane of symmetry. In fact, two of them. One bisecting the HCH angle, the other one bisecting the Cl-C-Cl. This molecule belongs to C2V. There are two vertical planes of symmetry. When you have that, this molecule cannot have optical isomers. Same thing in this case. If I have CHCl3, this is a C3V point group, like ammonia. And for that reason, it cannot have optical isomers. So anyone remembers for chiral centers, when do we say carbon is a chiral center? When it is?
Isn't it when it has 4 bonds with different attachments?
Correct. I mean, that means that carbon, whatever you have, should be bonded to 4 different functional groups, right? That is when you have a chiral center. That means there is no plane of symmetry around that metal. So tetrahedral complexes that are connected to 4 different ligands are a potential candidate to have optical isomerism. So let me give you an example of that. Suppose if I have a lead Cl Br Fi complex, which is tetrahedral, Cl, F, Br, and I. That can show optical isomerism because in a way that lead is chiral center. It's connected to 4 different groups. Okay, am I clear here, folks? This is when you can have non-superimposable mirror images, a condition for realizing optical isomerism. All right, so we know already linear complexes do not show optical isomerism, square planar don't. How about the octahedra? Octahedra, the answer is both yes and no. It depends on what octahedral complex we are dealing with. So let me show you an example of an octahedral complex that is basically an isomer, cis-trans isomer. In addition, it can also have optical isomerism. So let's talk about a complex that has a pairs of 3 ligands. So we'll talk about cobalt, NH3 twice, Cl2, Br2. Okay. When you have 3 such ligands, you can have 2 different arrangements. You can have cis or the trans. So let's do the cis isomer. So you have, so start with the trans one first. So if you have to have a trans, you have to have an NH3 here, NH3 there, Cl here, Cl there, a Br here, Br there. So I call this A. Now, if you were to take the mirror image of this, if you were to reflect this structure in a mirror, you'll get cobalt, NH3 there, NH3 there, a Br here, and a Cl here, and a Br there, and a Cl here. Are they superimposable by simple rotation or not? If you take this structure, put it on top of it, with a simple rotation, do you see how nicely they can be superimposed? So this is not an example of an optical isomerism. when you have 3 different ligands in a complex, each arranged in a trans geometry, that resulting complex cannot show optical isomerism because the mirror images are simply superimposable with a C4 or a 90-degree rotation. Let's look at the same complex in a different orientation. We're not changing the ligands, we're not changing the complex, we are changing the stereographic projection. So let me write down an NH3 here and an NH3 there, a BR here and a BR there, and a CL here and a CL there. What did I do now? I put all the ligands cis to each other, right? The chlorines are in the same edge, the ammonia ligands are in the same edge, and the bromine ligands are also in the same edge. So this is almost like a cis configuration. Now, if you were to take the mirror image of this looks NH3 there and BR, that is not going to change, but the CLs will be here, and a BR will be here, and an NH3 will be there. Those two are mirror images. Now you try to superimpose. Can they be superimposed? You cannot, because you have the 2 CLs and you have a BR and an NH3 here. So when you try to put that structure on top of it, it is non-superimposable, even with rotations. So when you have an octahedral complex with 3 pairs of ligands arranged cis to each other, then you can have an optical isomerism. I want you to compare this with the previous structure. Previous structure was superimposable with a simple rotation, but this cannot be. So it is possible to have isomerism, especially the optical isomerism, in coordination complexes if you have the pairs of ligands arranged cis to each other. Otherwise, no. Am I making sense here, folks? Okay. So basically, to summarize what we've been talking about, I would claim that if a compound is symmetric, then it may not show optical isomerism. Okay. Only asymmetric objects show optical isomerism. For that reason, linear and square planar complexes can never display optical isomerism. A tetrahedral complex can show optical isomerism if it has 4 different ligands. And octahedral complexes of monodentate ligands that are capable of optical isomerism only if they have 3 different ligands and they are mutually cis to each other. So that kind of summarizes our discussion on the various types of isomerism that is possible in coordination complexes. Any questions on this so far? Before I move to the electronic structure, which is the 18 electron rule, 14 electron rule, 16 electron rules. Anything not clear?
Professor Chari, I have a question.
Sure.
So with the optical isomerism, didn't you say like certain geometries don't have it? Which ones did you say that don't have it?
Linear and square planar.
Okay, they don't have optical isomerism?
They can never have optical isomerism because there's a plane of symmetry, right?
Right.
You have a linear molecule, it has a plane of symmetry. If it has a square planar molecule, regardless of how many ligands you have, because that plane itself is a reflection plane.
Thank you.
Any other questions, folks?
Professor, this may be a stupid question, but
I have a definition for a stupid question. Do you want to know what it is?
okay.
A question is stupid if it is not asked.
Okay.
If you ask it, it's not stupid. Okay, all right, go ahead.
All right. So you said that in order to show optical isomerism, you need to be non-superimposable and chiral. But chiral also.
No, chiral means non-superimposable. So the
Okay.
condition for optical isomerism is two structures are optical isomers if they are mirror images of each other, but non-superimposable.
Okay, got it. I was unsure about the chiral definition because it you needed 4 different functional groups attached, and in the molecule that we just did, we have 2 NH3s. So I was unsure about that.
Yeah, I can understand that because when you are in organic chemistry, you only deal with tetrahedral geometries, right? So when you go to the octahedral geometries and linear geometries, then suddenly your scope expands and you need to take into consideration several other factors, which is what I was going through here.
Thank you.
All right, excellent. Any other questions, so folks, so far? Are we okay? All right, so with that, then we will move on to what we call the 18 electron rule. So although complexes may look really different, it appears that in general, complexes that are favored follow what we call an 18 electron rule. If you count all the electrons of the ligands and the metal in a complex, and those that have 18 electrons tend to be really stable. Okay. An extremely stable complex is also the most useless complex because it will have no activity, like helium, neon, argon, right? I mean, these are all very stable gases. There's no chemistry. You can't add or remove electrons. But then the stability of a complex is attributed to the presence of 18 electrons when you combine the electrons of the metal and that of the ligands. So let us look at simple complex here. We'll start with the same complex that we started before. Methyl, PR3, PR3, CO, CO, and CH2 double bond CH2. That's the pi electrons of the double bond. How do you count the number of electrons in this? So the first thing we need to do is we need to find out what is the oxidation state of rhenium in this case, which we did this already before. Anyone remembers what the oxidation state was?
+1.
+1, wonderful. So when you look at the periodic table, how many valence electrons does Re+1 have? Those of you sitting next to the periodic table, or you can pull up the periodic table and looking at the configurations of manganese. Manganese and rhenium on the same group. So how many total number of valence electrons they have, and how many valence electrons are there when you have +1 oxidation state? Remember, these are all ND5 4s2 configurations, D5s2 configuration. In the case of manganese, it is 3d5 4s2. In the case of rhenium, it will be 5d5 6s2. So if I remove 1 electron, how many valence electrons this will have then? The neutral rhenium has 7 valence electrons, So if you have rhenium 1+, it will have 6 valence electrons. Is that correct? Yeah. And the methyl group, anionic ligands, it contributes 2 electrons. That is from the methyl group. All anionic ligands, halides, methyls, trialkyl methyls, or benzoids, hydrides. I'll give you a list of them during the end of this, but these all contribute 2 electrons. Carbonyls, trialkyl phosphines, all these contribute 2 electrons each. So since I have 2 carbonyls, and I have 2 PR3s, each PR3 contributes 4 electrons. Remember, phosphine will have a pair of electrons and phosphorus, right? Those are the electrons that we're talking about here. If I have 2 such functional groups, the total will be 4. And I have pi electrons of the ethylene. That will be 2 electrons there from CH2, CH2. So what's the total here? 6 from rhenium, 2 from methyl, 4 from 2 carbonyls, 4 from 2 trialkyl phosphines, and 2 from alkenes. So what's the total? When you add all the electrons, what do you have?
18.
18. So this complex is a stable complex. In fact, this is only one of those examples. There are many, many, many complexes that are stable when you have the 18 electrons. Okay. You understand how to calculate the number of electrons? Ligands contribute 2 electrons per each, and all of them, that should be 18. Of course, this is not always true. There are some complexes that are stable at 16 electrons, 14 electrons, but in general, 18 electrons seems to be a good guiding principle to predict the stability of a complex. So with that, I will give you a list of all the ligands that contribute 2 electrons, and some anions contribute 4 electrons, and some can contribute electrons. So let me write down a list of all these things here so that you will be able to use that list to, so first we call neutral 2 electron donors. In this category, we have carbonyls, alkenes, alkynes, and nitriles. You can also have anionic 2 electron donors. Contribute only 2 electrons. Those are your halides, chloride, bromide, iodide. Those are the things on methyl, CH3 minus. And you have trialkyl methyls, Cr3 minus. You have phenyl, negative group. You have a hydride, that is negative. So these are all the anionic donors that contribute 2 electrons each. You can also have anionic 4 electron donors. the anionic 4 electron donors are allyls C3H5 minus and oxides O2 minus, sulfides 2 minus, and Cr2 alkyl diamines Cr2 minus. You can also have alkoxides, which are bridging in the sense the ligand binds 2 different metals. So that's another way of achieving complexes. So far, only when the metal is all by itself, but you can also have what we call bimetallic complexes, when you have 2 metals joined by a ligand. If you have an alkoxide ligand, then that one, if it is binding, contributes 4 electrons. Similarly, SR minus tylide bridges. These are tylides. Bridging again. And then phosphor2 minus. These are all, when they're present in a complex, these ligands contribute 4, not 2. Finally, we have cyclopentadienyl, which is anionic, but 6 electron donors. Cyclopentadienyl, Cp minus, suits 6 electrons. These lists are available on the internet. You can always go into the sites, figure it out, but I thought maybe I'll just put them in one place. So whenever you deal with a complex, you will be able to know how many electrons this compound has. So let's work out some examples in the last 2 minutes. Last few minutes that we have. But is this clear to all of you folks? Okay, so using this, let's figure out let's say if I have MnO4 minus. You all know about permanganate, right? Potassium permanganate. So permanganate minus, it's a complex. Where manganese is bonded to 4 oxygens. So how many electrons this complex has? What's the first thing that we need to find out? The oxidation state of manganese here. How much is it? What is the oxidation state of manganese here?
Should it be +7?
You're absolutely correct. So how many d electrons manganese 7 plus has? Manganese is 3d for manganese 7 plus, the total number of electrons should be 0. Am I making sense? And if you have 4 oxygens, oxide, how many electrons oxygen donates? In the table that I gave you, oxides are 4 electron donors. So there will be 4 times 4, 16. So MnO4 minus is a 16 electron complex. Am I making sense here, folks? Okay. Let's take maybe a couple of examples where something very similar to an exam question. That obeys 18 electron rule. Okay. Now, based on this, what is the identity of the metal? It could be titanium 2+, manganese 3+, cobalt 2+, vanadium 4+, or copper 1+. Choice A, B, C, D, and E. There are 7 carbonyls. This so what should be the oxidation state of the metal here then?
+1.
Hmm?
+1.
+1. Sorry. So let me write down this one here. So that metal should be +1. All right. How many electrons now we have here? 7 carbonyls. How many electrons? 7 times 2, right? Carbonyl provides 2 electrons. That gives it 14. If it is 14, for it to have 18 electrons, how many electrons should be in the metal in the +1 state? (18 minus 14), right? 18. So which metal in its +1 state has 4 electrons? Remember the examples we gave was titanium, vanadium, cobalt, copper, and chromium, let's say. Which of these metals have 4 electrons in the +1 configuration? Remember we did all the stuff before, electronic configurations? So what's your choice there? I've given you titanium, vanadium, cobalt, copper, and chromium.
Is it copper?
Copper 1+ has, looking for a metal which has 4 electrons in its +1 state. Copper has 10 electrons. Remember, copper is 3d10 4s1, correct? So copper 1+ will have 3d10, which means 10 electrons. Cannot be copper. What else?
Vanadium.
Michael, you are absolutely correct. It's vanadium. Because if you look at vanadium, it is argon 3d3 4s2. Right? So neutral vanadium has 5 valence electrons. We're looking for a metal in the +1 state. So vanadium +1 will have 4 electrons. So the correct choice for this is going to be vanadium. So if there is an unknown complex like this given to you, and if they say it obeys 18 electron rule, then based on all these calculations, you should be able to figure out what the unknown metal is. I'm afraid that's all the time we have now. Maybe next week, couple of more examples on the 18 electron rule, 16 electron rules. And we will also touch base on some of the acids and bases. Okay, which is what we will try to do next week. I'll try to put in a video for the acid-base chemistry, and between whatever I'm uploading and whatever I'm doing in the class, you will have a good idea about all this. Any questions so far before we leave? All right, if there are no other questions,
I have a question actually.
Yes.
When is the exam?
We'll have 2 weeks from now.
Okay.
I'll let you know by next week. All right. Yeah. Again, I told you, right, the exam will cover molecular orbital theory, right? And coordination complexes and the point groups. And maybe 1 or 2 questions on the acid bases, depending on how far we go next week. If there are too many questions on coordination complexes, we may have to skip the acid base for the final exam. But otherwise, we'll try to have 1 or 2 questions there. Is that okay? All right. If there are no other questions.